Good morning, class. Good morning, Margie, and the rest of grade 10. Please review this video. Okay, I only have Margie in my class, and the rest are absent. I think we have only 2 students online, so most probably the rest rely on Mojo, so it's okay, right? Let's move now to Amonton's law. Okay, Amonton's law is talking about pressure and temperature, the relationship between pressure and temperature. Okay, Guglielmi Amontons, this is between 1663 to 1705, investigated the relationship between pressure and temperature, okay, in gases. He discovered that the pressure of a fixed mass of gas and a fixed volume is directly proportional, okay, to absolute temperature. He discovered this while building an air thermometer, okay. So Amonton's law can be expressed mathematically because this is a law, okay, with P is equal to CT, or P over T is equal to C, or constant, okay? Or constant is equal to P over T, okay? Where P is equal to pressure of gas expressed in millimeter of mercury, atmospheric pressure, or torr, okay? While T there is actually your temperature of gas measured in Kelvin, while C is the constant, okay? In some chemistry books, the pressure-temperature relationship is referred to Gay-Lussac's law. Okay, some of them, or some of the books are actually talking about Gay-Lussac's law. They're actually the same with Amonton's law. Okay, comparing substances under two different sets of conditions, the law can be written as P1 is over T1, or is equal to P2, your final pressure, over your final temperature. Okay, P1 over T1 is equal to P2 over T2, where P1 is the initial pressure and T1 is the initial temperature, okay, while P2 is the final pressure and T2 is the final temperature. So as easy as that, a simple mathematical equation actually. The relationship between pressure and temperature can be explained by the kinetic molecular theory. So we actually discussed kinetic molecular theory in higher years, like in senior high. Okay, grade 10 is the introductory for the kinetic molecular theory, which is the gas laws. Amonton's law explains the following concepts or phenomena or applications. There are more flat tires during summer. This is because, again, the temperature and volume. The temperature is high during summer, thereby causing increased pressure inside the tires. Okay, temperature and pressure. Throwing an aerosol can into fire can cause it to explode. Okay, high temperature causes gas in aerosol, air, or aerosol can to exert more pressure. Pressure is adjusted in tires before a trip. Okay, we actually lowered the air inside the tire before a trip simply because, again, the temperature and tires will actually go high when you are actually using that one. The flexing of tires while driving increase the temperature of gas inside the tire, thus increasing the pressure inside. Okay. Dipping distended ping pong balls in warm water. Okay, hot water raises the temperature of air inside ping pong balls, thereby causing gas molecules to move faster, which in return increase pressure, and again, your ping pong balls will return to its original shape. Okay, distended, mean to say it is actually lumping. Okay, so when you put it in high water or in hot water or warm water, it will actually return to its original size. What else? Operation of the pressure cooker. Pot pressure cooker is a well-sealed pot. Okay? It does not allow steam to escape. The steam builds and creates pressure that is about 10.34 newtons per square centimeter. Water under the pressure or high pressure boils at the high temperature of 121 degrees centigrade or 250 degrees Fahrenheit, then the normal boiling point, which is 100 degrees centigrade or 121 Fahrenheit. Due to the too high temperature, the food gets cooked faster. The pressure cooker contains mainly 3 parts. We have pan, lid, and its accessory, of course. Okay. This is the usual use or the practical applications. Let's move now to the combined gas laws. Combined gas laws are actually talking about the three laws that we had just discussed. Okay, Boyle's law, Charles' law, and Amonton's law. Okay, combined gas laws can be expressed, okay, as PV over T is equal to C. Okay, again, with what is P again? Pressure. Okay, V is volume, C is constant, and of course, T is time, or temperature rather. Pressure, P, V is volume, and T is temperature. By comparing some substances into two different sets of conditions, okay, P1 times V1 over T is equal to P2 times V2 over T. That is actually the formula over T2. So initial, okay, initial pressure times initial volume over initial temperature is equal to final pressure times final volume over final temperature. Okay. There are standard set conditions. There is a standard set of conditions for experimental measurement to enable computations within sets of data. Okay. This is referred to as standard temperature and pressure, or STP. Okay. It is actually included in the STP. Okay. Do you have any questions so far before we continue, Margie? Questions so far? Dimitri is here already? Hi, Dimitri. Can you hear me, everybody? Can you hear me? Okay. Let's move now to Avogadro's law. Okay. Avogadro's law is actually talking about volume and amount. Okay. Let's take a look at the relationship between volume and amount. Amadeo Avogadro, this is in 1776 to 1856, proposed that equal volumes of gases at the same temperature and pressure contain the same number of molecules regardless of their chemical nature and physical properties. This is known as Avogadro's law. Okay, Avogadro is actually concerned on the volume and the amount, or the number of molecules. Okay, mathematically, it is expressed as V over N is equal to C, or C is equal to V over N. What is the V there? V stands for volume, and N is the number of molecules, is equal to constant. Okay, one molecule of any gas consists of 6.02 by 10 to the raised to the power of 22 molecules, known as Avogadro's number. Avogadro's number is actually presented during your lower years. That I think this is in grade 9. Okay, and you'll be using the Avogadro's number even in senior high and college. It is the number of molecules of any gas present at a volume of 22.4 liters. In summary, 1 mole of an ideal gas, okay, occupies 22.4 liters at STP. Okay, standard temperature and pressure. The volume is referred to as molar volume. Okay, ideal gas law. Okay, recall the three bases of laws, or base laws. We have Boyle's law, which is volume is equal to P, or pressure. Charles' law, which is volume, volume to temperature, wherein N is constant, or the number of molecules is constant, and pressure is constant. Okay, and Avogadro's law, we're talking about the number of moles here. So this relationship can be combined in a single relationship, wherein V is directly proportional to R. R there is the proportionality constant. How can we measure the proportionality constant? Okay? Proportionality constant can be measured in N, which is your number of moles times temperature over pressure. Okay? Rearranging, we have PV is equal to N R times T. Okay? Where P is the pressure expressed in ATM, or atomic atmospheric pressure. V is expressed in liters because this is volume. Okay, N is moles, the number of molecules. Temperature, T is actual temperature expressed in Kelvin, degrees Kelvin, and R is the gas. Okay. Remember that R there is the proportionality constant. So this is the measurement of, or this is how we can actually get the R. Okay. The R value is computed in the following. Okay. This is the R, the one that I'm telling you a while ago. PV over NT, right? Okay. Pressure times volume over the moles times temperature. Okay. As you can see, we are actually talking about the constant here. The constant mole or the liters is actually 22.4. That is according to the according to the constant proportionality. Okay, over 1 mole. Okay, amount, pressure times volume. Okay, over N, 1 mole, and the temperature in Kelvin is, this is the constant, 273 Kelvin, or equivalent to 0 degrees centigrade. Okay, how can you convert centigrade into Kelvin? You just add 273, and that's it. That's the degrees Kelvin. Is equal to 0.021821 liters at per ATM, or atmospheric pressure. This is ATM over 1 mole. This is mole per Kelvin. So the constant there, or R, or proportionality constant, is 0.021 liters per ATM, okay, over mole per Kelvin. This is supposed to be one here, but again, if you're going to solve scientific problems and computations, you can just put the units used there instead of putting one. Okay, the ideal gas law is defined as one in which all collisions between atoms and molecules are perfectly elastic and there are no intermolecular forces acting on it. And that is actually under the ideal gas law. So meaning to say that all of these interactions, there is no intermolecular forces that acting on it or outside force that acts on it. Okay. At normal conditions such as standard temperature and pressure, most real gases behave qualitatively like an ideal gas or gases. Ideal gas model fails at a very low temperature and very high pressure when intermolecular forces and molecular sizes become important. If there are some interaction with intermolecular forces, tendency is it actually breaks the ideal gas law. Let's move now to Dalton's law of partial pressures. By the way, do you have any questions so far? Dimitri? Questions? Okay. No worry, we have actually a summary of this. Dalton's law of partial pressures. John Dalton, this is in between 1766 to 1844, found that the pressure exerted, okay, by the mixture of gases, meaning to say this is a different sets of gases, is equal to the sum of partial pressures of gases present. This is known as the Dalton's law of partial pressures. Let's take a look at this one. In equation, the pressure of mixture can be summarized as pressure total, or total pressure is equal to P1 or pressure 1 plus P2 or pressure of gas 2. Okay? The total pressure, we're in PT, or total pressure is equal to P1 or pressure of gas 1, first gas, and P2, pressure of gas 2. This is just the summary. Total, wherein the total P, the PT is the total pressure of the mixture of gases expressed in millimeter of mercury, ATM or torr. Okay, the rest are the pressure of gases from gas 1 to gas 2 and so on. So if you have 3 gases, you can actually add another gas. Okay, that is according to Dalton's law of partial pressures. I think we discussed a lot. Hopefully by next meeting, I can give you computations, some of the computations of this. We will apply the Avogadro's law, the combined gas laws, Amonton's, Boyle's law, and Charles' law with regards to the computations. Okay, let's have the activity by next meeting, hopefully. Okay, do you have any questions so far? Questions so far with gas laws? Oh, by the way, with your project, since you're talking about gas laws, okay, your project for this school year, we will be dealing with gas laws. Okay, how can you make your project? This is based again in your first module for the 4th quarter, which is gas laws. Okay, you just need to choose some of the concept there and create a learning resource material out of it. What are these learning resource materials? Okay, create a learning resource material out of our topic for 4th quarter, module 1, again, which is gas laws. Okay, illustrating science concepts that we had discussed. This includes, but not limited to, the 2 categories. You have digital outputs and physical outputs. What's with the digital outputs? For digital outputs, you can actually make blogging, okay, and video documentaries. This is narrated, okay? Blogging and video documentaries by you, okay? How about the second category? We have the physical outputs, okay? I'm encouraging everybody to, or everyone, to make physical outputs, since this will have the biggest grades, okay? This will have the biggest grades pertaining to outputs. Make it as attractive as possible with your own creativity and any materials of your choice. Please take note that this is your output for this school year, and it will be exhibited as soon as we are allowed to do so. Okay, what is actually included in the physical output? We have 3D of science concepts. Number 1. Number 2, diorama. You can make your own diorama. Number 3, miniatures of science concept. And number 4, the actual science concept if possible. Okay. Again, this will be your output for the school year. I will be there in school. I'll be in school every Friday to check your outputs. Right? Deadline. Okay, I will give you ample time to do your project. It's okay with me. The deadline will be May 13. Okay. Today is April 7. So we will have more than 1 month to do your project. Okay. Don't worry, I will also give you updates, okay, in your LMS. I will be uploading something in your LMS for your project, and even the offline also can receive it through their modules. Right? Do you have any questions so far, Dimitri? Questions so far? All right. I think that will all for today, class. Expect for some examples by next meeting, and hopefully we can also have some of the activities. Thank you for participating, Dimitri. I only have Dimitri here, and of course, Margie. Okay, have a nice day, everyone. Take care. Bye-bye.